So in if you Google there are some areas where people classify the systems into the single agent system and the multi-agent system. Well, the single agent system is that well, there's a system, whether there's a single person, units, whatever, and then he or she tries to optimize some control variables in order to optimize the system, whether metric can be various things, like the throughput, energy, delay, whatever. The system, or reliability, whatever. But there are some other areas where the multi-agent systems, where there are multiple players, okay? And then there are two ways of interacting with each other. For example, multi-agent players are working together in order to maximize this global objective. What's an example? Example is that, well, KT, for example, or SKT, deploys the multiple base stations all over the places in Korea. And obviously, the one operator can control multiple base stations towards their objective. They can control every components at their own. That's one behavior. Now another behavior is that each agent or the player has his or her own objective or goals. And that's actually why the game theory or what the game theory keeps saying. It's actually every agent are selfish, rational. They have their own objectives and so on. Okay? So what we are dealing with is this area. And this is where we need game theory. So there are some books about the multi-agent systems, and then the game theory, presentations are very long in the multi-agent system book. And after that, there's some topics or the contents about the learning methods. I have one book. If you Google, then you can see this title of the book, like multi-agent systems. Then you can see the game theory as well as the learning framework and so on. So game theory is not something that only like economists or some specific area people are using. Is that actually what's the area of this? The CS people are doing this kind of thing. Also, the EE people, operations research people are dealing with this system. Right. All right. So let's move on to another learning called first reinforcement learning. So the reinforcement learning is something you can see the classical machine learning textbook. Okay. And for example, if you open the classical machine learning textbook, then always in the chapter 1, well, the learning framework can be classified into three categories. First is the supervised learning, another is the unsupervised learning, and the third is the reinforcement learning. And then we are actually taking the principle of this reinforcement learning, but the game theory, but the machine learning textbook starts from the scenario where we have just a single player or a single agent systems. So they start from the Markov decision process definition, and then if we don't know the parameters of the Markov decision process, then actually we can do some action and then get the reward and change the action by doing this reinforcement. Right? But here in the game theory class, what we are doing is that it's actually we are thinking about the multi-agent cases. Because there could be like 2 players, 3 players, and so on. But probably we can transfer the rationale of the reinforcement learning to the multi-agent cases. That's actually what we are covering on. So what's the basic idea of the reinforcement? Reinforcement Reinforcement means that in Korean 재광화를 시킨다. 더 강하게 한다 뭐 이런 뜻이잖아요. Reinforce. So the basic the philosophy of the reinforcement is that from the experience I do some action, and suppose that I get a higher payoff or higher utility, higher reward, then I'm going to reinforce that action, meaning that I'm going to more frequently use that action in my action choices thereafter. That's what we mean by reinforce. Okay? So if you go back to the trial and error learning, do they include the concept of the reinforcement? Maybe or maybe not. Right? So the environment is the players only knows his past choices and perceived utilities. Of course, I mean the action, including the action. We assume that we know the past choices. It's not a big thing. So using the information, each player tries to learn a strategy that maximizes expected future reward. And you can exactly see the same sentence when you open the machine learning textbook about the reinforcement learning. I want to maximize my expected reward, sometimes under some discount factor. Right. So I was a little bit tired, just to copy the PDF text to the material. But believe me, I mean, this is a much nicer version of my previous lecture. The previous lecture is like 3 years ago. I spent a lot of time on modifying and improving the lecture slides. But at this time, I was a little tired. But I did this. I made this. Okay? I didn't just copy and paste and then read. Okay, I didn't do this. I added some interpretations. Okay. All right. So in this book, they introduced two algorithms. First is the Mostella algorithm, and Bush and Mostella algorithm. Another is Arthur's algorithm, which is more recent. I believe that there are some other algorithm which inherits the philosophy of this reinforcement learning. I mean, think about that. AlphaGo. AlphaGo is the game between two players. So the algorithm in the AlphaGo actually can be regarded as a reinforcement learning in the game context. Right? So if you maybe have a chance to take Professor Jung Se-young's class about deep learning in AlphaGo, and in the last part, he explained the game, like just one slide, the game tree stuff, and then he just moved to the reinforcement learning algorithm, which is adopted in the AlphaGo game. But their main question was that how can we get the reward function, Q function for example, in a very large scale reinforcement learning in a game theory context. So Q value is something like some function that can represent how well am I doing. But since the AlphaGo case is that it's really large scale. Large scale means that what? There are many choices or combinations of choosing the actions and so on. So what they are doing is that they do some approximation in evaluating the Q value. How do we do the approximation? Well, they apply the deep learning framework. That is called the deep Q network, DQN. Or sometimes they apply something called the policy gradient algorithm, something like that. That's the story of approximation. What I could not do so far is that, well, obviously, since we're talking about the reinforcement-based learning in the game theory context, somehow we could find the connection between the reinforcement learning in the game theory context with the algorithm that is implemented into AlphaGo. There should be some connection, right? Because the AlphaGo, again, that's a game between two players. So that's also the reinforcement learning game learning in the game theory context, as far as I understand. But still, I'm trying to find the connection. So we should be able to talk about those AlphaGo algorithm in this class. But when I look at the textbook, I can see only this like old style algorithm like Bush-Mostella and other algorithms like Arthur's algorithm. So I'm currently studying source of that. So before the semester ends, if I have some answers, let me give you some special lecture about how should we understand the reinforcement learning algorithm in the AlphaGo from the perspective of the reinforcement learning in the game theory context. So there should be some connection. Okay. I mean, of course, that's a large scale algorithm, but in addition to those differences, there could be some connection. So I'm still studying, thinking about what's the connection, how should we interpret the AlphaGo algorithm in this context also. So before I become more perfect about the contents, let me first briefly cover the algorithm in this book. Okay. And this book was published like 5 years ago, so it's not an old book. So let me give you some story later. Okay. But anyway, let's cover the algorithm in the book. All right. So you can just feel or have some taste about how the algorithm works. I mean, how the reinforcement idea is implemented or realized in that. Think about the concept of the reinforcement. Okay? Whenever I get a higher payoff, I'm going to reinforce that place. Okay? The setting is the game, players, the action spaces. Okay? That's everything the same. Where let's say the xj, aj is the probability of the player j's to undertaking the action aj. Okay. It's like probability, mixed strategy or probability distribution. And each time t, each player j chooses an action aj, comma t. The player j and the time t, and the computes are something called the stimulus. 우리말로 하면 자극 이런 거죠. Stimulus as far as j, comma t for the action just chosen, for the chosen action like AJT according to this formula. So it means that okay, for my action choice like AJT for example, I'm going to at each time I'm going to compute something called the stimulus. Okay, so what is a stimulus? Stimulus, if you read. Interpret this thing. Stimulus is defined as the uj, comma t. That's the utility value that I got by playing the action aj, t. Okay? And mj is something called the aspiration level. The aspiration is often used in the game theory, especially the game dynamics. Aspiration is 우리말로 뭐죠? 열망 그런 거잖아요. 그랬으면 좋겠다 뭐 이런 거죠. 그래서 열망에 비교해서 내가 얼마나 차이가 나는가. 내가 열망이라고 하는 거는 거기 갔으면 좋겠다 뭐 이런 뜻인데 거기에 비해서 얼마나 차이가 나는 거 그런 의미의 stimulus. So stimulus means that how much difference that how much do I differ from the something that is called this aspiration that I'm targeting at in some sense. Okay? So the stimulus can be interpreted as how am I satisfied about a particular action measured by my aspiration level. Right. Okay? Right? And what? The denominator is just a kind of normalized term divided by some supremum, the maximum of those things. Right? Okay? So that's the basic idea. So at each time I play for the action that I play, I compute the stimulus. And stimulus essentially quantifies then how satisfied I am about my choices. Okay? And then what it does is that I'm going to now choose my action, or this is a what? It's not my action, it's mixed strategy. It's a probability distribution. Probability distribution of AJ action at time t plus 1 in this manner. Right? So what's the updated equation? Well, this is my old probability distribution, or old probability for the action AJ. And then, depending on my stimulus, I'm changing or updating my probability distribution differently. Okay? So the large stimulus, which means the what? Large stimulus means that it's like large regret, in some sense. Okay? So in that case, I'm going to assign larger probability for that action. So how am I going to apply that kind of philosophy to my updated equation of my probability distribution? Well, the stimulus is zero than or equal to 0, larger than or equal to 0. Then what does it mean? Then this is essentially positive. So my utility is above my aspiration level. In many cases. So in that case, what I'm doing is that I'm doing or giving or adding more probability for the action because it's good. Okay? So my old probability plus lambda j, where the lambda j is a learning rate, or you can say that like what optimization for what step size. The learning rate, step size, like 1 over n, 1 over t, or something like that, in order to make some convergence. Okay. So add my amount of the stimulus and 1 minus my probability, where the probability, this probability is the choosing probability. This is not the probability that I'm not choosing the probability. So this should be the plus. And if the stimulus is minus, then what? My utility for that action is below my aspiration level. So what I'm doing is that I'm going to decrease my strategy, the probability distribution, using the learning rate and this stimulus should be a minus, and my old value. I mean, okay. So the key thing about this algorithm is that we set the aspiration level, and then I'm going to update my probability of choosing some action is actually follows from the value of the stimulus. So, now what is the question? The question is, how do we set the aspiration level? This always comes up, right? So whenever, I mean, you have some experience of, okay, if you do some project or research, then the algorithm that you frequently choose is that if some value is above some threshold, I will do that. And if some value is below the some threshold, then I will do that. So the question is what? How are you going to choose the threshold? Well, the threshold, I'm doing that, this, and so on. So I was really wondering about how to set the aspiration level, but there is no description in the book. But how to set the threshold, and somehow let's assume that that aspiration level is chosen appropriately. We need to look at the paper, and then this is the algorithm in 1955. It does not say that it's a bad algorithm, but obviously there could be a better algorithm after this. It's good to know that this. Okay. The important thing is what? Important thing is that, okay, where is the reinforcement philosophy here? So if you think about that, okay, I measure the goodness or the badness of my strategy choice using the aspiration level. And then if I have a good value, where the stimulus is positive, it means that, okay, I choose that action, and that action is really good. Gives me high payoff. Then I'm going to reinforce. And this is a reinforcement, right? And this is the reinforce. This updates equation actually means the reinforce. And then I get this probability distribution, and ultimately what I'm going to do is that I need to toss a coin and choose one deterministic action. Choose the one action deterministic. So I get the probability distribution, and then do some random choice according to or the following that probability distribution. And this is the part that we actually do the reinforce. Alright, so for the all reinforcement learning algorithms, we prove something, and where the theoretical tool is something called the stochastic approximation theory, where we need some knowledge about the probability theory as well as the differential equation and so on. Okay. Obviously, I'm not going to go to the details. So if you're interested in, please study the stochastic approximation, which is one of my main mathematical tool in some researches. Let's look at other types of algorithms, which is called the Arthur's algorithm. So the Arthur's algorithm, again the game. K is the players, AI is a set of strategies, and then utility is the function from the action to the real number. But in this book, well, they assume that this utility is a random variable. That happens. Okay. And so that's why the large UJA, they use some tilde. Okay. And that's the notation that I don't like. Why do we need to use tilde? Why not just U? Anyway, the small UJA is expectation of those random variables. Right? I mean, the utility can be obtained in a random manner because of the randomness of the nature and so on. That's just a more general situation. Now, players are repeatedly playing the game, and each time T under reinforcement learning in this algorithm, each player J is assumed to have a tendency here. Okay, oh, I see. So they use something called the tendency. So in the earlier algorithm, they use something called the stimulus. Here they use something called the tendency. 그걸 할 경향, 정도 이런 뜻이죠. Where that is denoted by the alpha JT of AJT. Okay? And that probably quantifies how I am happy about that action. Probably. And tendency to each action. Okay? Now I'm going to explain how this tendency is maintained later. And XJT AJ is the same thing. It's a probability that I'm going to choose AJ. It's basically the probability distribution or the mixed strategy, if you like. An action and time t, right? So that's the model, right? And the algorithm is, yeah, I drawn underlines here. It's a big effort. Okay, so the algorithm is that the question is that how can we compute this probability distribution? Because once we got this probability distribution, I toss a coin and choose some particular action and play that action. So now I'm going to explain how we update this AXJT. Where when we just look at this the equation first, that is the summation of the old probability plus some UJT, maybe utility, I don't know. And some indicator function where I'm playing the AJ at time t plus 1. Alright, good. So let's go back and try to what it means. Okay. So for that, we're going to consider this XJ probability will be determined by some intermediate steps. So let's look at the intermediate steps. First, we're going to compute the PJT-AJ. PJT is different from the XJ. Okay? PJT is again the probability distribution, which is the function of all my what is this? What is this? What is this? What state?
갑자기 튀어나왔어. 이거 설명해 주시면 제가 상을 드릴게요. A 아니야, A? 그래서 갑자기 튀어나왔어. I guess it's typo. S가 없어. 어? There's no S. S가 좀 밑에도 있네요. Where's S?
Alright. Okay. That's fine. Okay. We can explain without S. Right? Because the key meaning is important. So whatever it is, some maybe history of what happens in time t. Okay. So I'm going to construct some PJT of AJ. Is that we're going to consider this mapping as some special case. Well, in some special case, we're going to look at this one. Okay. Because this is a probability distribution, the denominator part is just normalization. So let's ignore that. And then probably important thing is C. 봐봐. 여기 ST, 이거 AJ는 똑같은 거잖아. 아니, 물론 이거 인덱스로 사용했으니까 뭐 그렇다고 치고, 이거 뭐야. Okay? So normalization term, okay? And then if you get, this probability is proportional to what? The tendency. And then AJ is to the gamma power. Alright, so this PJT probability is proportional to the tendency, where the probability we can quantify the tendency or interpret tendency as the number that how am I happy about that action, and then the actions AJ to the gamma power. What's the meaning of the AJ to the gamma? Alright, so let's read. So now in order to complete the reinforcement learning algorithm, what we need to do is that how do we update the tendency? I just mentioned that the tendency is just quantified that how satisfied I am about the action AJ. So here, in the simple model, this is expressed as if the player J takes the action AJ. If I take the action AJ in period, then his tendency for AJ is increased by the incremental amount equal to his realized utility. I see. So the how 이걸 수식으로 써주면 얼마나 좋아. So how the tendency is maintained, where the AJ, if you read that, the player J takes an action J in period T, for example, then his tendency for AJ is increased by the increment equal to his realized utility. Meaning that if I have an amount of the increase in the utility, then I'm going to add the same number to the tendency. And also it's possible that my utility decreases, then the tendency also decreases. Right? Right? So if I look at just the number about the tendency AG, tendency alpha J, what happens is what? Okay, I choose AJ. What happens if my utility go up? Then my tendency number go up. But it's possible that even if I choose the same action, my utility can go down. Why? Because my utility is the function of other guys' strategy. And then my tendency go down. So if I look at the number tendency, like for example, that's a large good number, that means that in overall cases, choosing action J is a good choice. Right? Because I increase and decrease and increase and decrease my tendency based on the utility that I got by playing a J. Why sometimes plus, why sometimes minus? Because my utility is the function of the strategy that is chosen by others. Okay? So I just stack up some histories about my experience and how happy I am about choosing AJ as a function of other guys' choices, but I don't know what strategies are chosen by others. So I just record some number about AJ. That's the tendency. Right? So the PJT of AJ is roughly in proportion to the tendency. Okay? And then what I'm doing is that UJT is the random utility, because we modeled this game as the case where I get as a random number and utility. Random utility obtained by player J in time in period T. So 엄청나다. 왜 PJT가 갑자기 사라졌지? 이거 XJT 아니야? 이거 뭐야? X underbar, what is the X underbar? Please don't blame me. Okay, good. Okay. 완전 뒤집어지구나. So we need to define how to update the tendencies, where the tendency is denoted by the vector of x underbar t. Okay. 잘한다. So they use the tendency using the notation alpha, and the vector notation is x underbar. That's a good notation choice. Okay. Alright, so x bar t is a tendency vector. Probably they should be written as like alpha underbar or whatever. Right? So let's interpret the text. Okay? This should be the alpha, like alpha, all alphas like tendencies. And then I guess this S means that the actions of all histories, things like that. Okay? And this P should be something like XJT. Because there's no P here. I'm looking at where's P? There's no P here. Okay? So this is an X. Okay, let's clean up. Right? 프린티드 텍스트 이런 일이 벌어질 수 있냐고? 벌어질 수 있어요. 내가 볼 때 이거 쓸 때가 잡았어요. So this is an X, this is a tendency, okay? So that then makes the story, okay? So so this is an X. X is proportional to the tendency, but the part that I don't understand is this part. AJ to the gamma. What is this AJ to the gamma? AJ is just action. So it can be like 100, 1000, or what? Umbrella? No umbrella. There should be some conditions about the action spaces and utility value. For example, here, look at that. We can write the updating rule as the new probability is updated by 진짜 이거다. 그러면 이렇게 계산하기 말이 안 되잖아요. 왜냐면 이렇게 업데이트하면 이렇게 계산할 이유가 없잖아요. So this is a random utility that I got. So what this means that I'm going to update my probability using this rule, where indicator function is that, okay, if I play the AJ, then this becomes 1, and UJT is the utility value that I got by playing AJ. So if this is a minus, then I'm going to go down. And if this is a plus, I'm going to go up. That's fine. Okay? Then when we interpret this equation just according to this text means that why do we need to compute this PJT or whatever the XJT? Because all the values of XJT plus 1, XJT plus 2 is updated in this way. Why do we need this? 이 페이지는 내가 정말 알아봤어요. 당연히 읽어보면 해석될 줄 알았어요. really confusing, right? Okay. So I'm trying to find the R-factor algorithm in other paper or maybe the other material. Let me clarify that later. It's very confusing. Notation is bad. So let's just get some lesson and what these guys are doing. So what these guys are doing is essentially that they sort of introduce the concept of the tendency based on the utility increase and decrease. And then the question is, how am I going to adopt those changes in choosing my probability of choosing some particular action at the next time slot? And that's actually how this reinforcement idea is realized in this algorithm. But the algorithm is not here. Sorry. All right. Don't ask me the question.
It is
Wait,
not about detail.
Okay.
But can you say that in game theory, the reinforcement learning algorithms are like applying the multi-band format on learning dynamics?
Multi-band problem is not the game theory concept, setting, right?
Yes.
Because I just play the single agent system, right?
Yeah. But I'm asking this.
Oh, I see. So your question is that, okay, so well, he knows something about the multi-band problem. So in the multi-band problem, there are various good families of the algorithm, like UCB, KLUCB, or some other algorithms. They actually take the trade-off between the exploration and the exploitation algorithms. His question is that, why can I see those types of or similar form of the algorithm in this game, in this context? Okay. That's your question, right?
Yeah.
Okay. That's a good question. That's actually the question that I also got. So that question is also related with the question of why not like alpha boost algorithm in this game theory context. Because I cannot see, I cannot see the exact overlap between this type of the algorithms and the AlphaGo algorithm, and also as you mentioned, like UCB style algorithm.
I'm asking the question about multi-band because the algorithms you presented on the reinforcement learning slides are only doesn't depend on state, because there are no parameter like what I consider to choose action. In my knowledge, when I studied reinforcement learning is like I have a state, and at that state I have a policy to choose such an action. But these algorithms doesn't have like state, but they just sampling the about rewarded value of actions and just choosing an action.
All right.
And for me, that is like multi-dependent, only the part of the reinforcement learning. So I asked.
Okay, so let's divide the questions. The first question is that in a normal like reinforcement learning, we define the state, and in some state I choose some policy, where if I choose some policy then I get a reward, and based on the reward I take some another policy by like changing the state and then and so on, right? That's the first question. Let's consider the second question later. So in terms of the first question, it's very difficult to define the state. The question is why? Well, I can define my state based on only my information. Like, okay, the action that I choose in the previous state. But I cannot represent the entire system state because I don't know what other guys chooses the strategy. And in that sense, well, this guy maintains a state, like his own state. Okay? And then what he can try his best is that, well, they sort of try some actions and then they sort of make some conjecture about, oh, choosing this action is a good choice or a bad choice. Well, we're not sure, right? So what we can do is that we just record some numbers about some estimation about the good news or the bad news of some actions. And then the good news or the bad news is actually the function of other guys, all the choices. But I cannot see those things. And that's the thing. And so just moving to the second question. So you said that, all right, since I don't know other guys' states, it looks like a multi-argument problem. Because, well, I know my state, because I don't, right? That's what's your question, right?
Because I know not my state, there are no such a state definition in these algorithms.
Right. But if other guys' choices are not strategic, but random is something like the property from the sky or the nature. That is almost equal to the multi-argument problem. But the thing is that other parameters they are moving or they're changing their strategy from the goal of maximizing their utility. So it's not purely random. Their choice is also the function of my choice. That's the key difference between the multi-argument bandit and this problem set.
Then in what part these algorithms does consider those kind of relation or, I mean, rotationality due to my action change and others' interaction?
Well, so that's why what we can do is, for example, like the first algorithm, like Bush's algorithm or this algorithm, the key philosophy is the same thing, right? Again, this is my action. A1 to AN. This is my action. This is my action. So I record some number. The good is or the bad is. So this is really a 3 star. This is second 2 star. This is 1 star. This is 2 star, and so on. That's the tendency, and that's the stimulus. Well, this is a very, very rough estimate about these actions. Sometimes if I choose the 3 star action, it's possible that I get a very, very low utility. Because it's a function of other guys' choices. But then why do I mark the 3 stars? Where sometimes I get a very low utility, but in many cases I get good utility. So overall, I will mark this as a 3 star. And that's what the tendency is capturing, and that's what the stimulus is capturing. And if you think about this problem, probably this is the only thing that we can do. Because I don't have any information about others. Right? So all the algorithms is that, okay, goodness of the badness is quantified by some 3 star, 2 star, some number. And then I'm going to choose my, choosing the probability that I'm choosing AJ is some function of this 3 star, 2 star story. And then choose the action based on this probability. That's it. The question is, what is the rule? Well, they can think about some rule, like aspiration level or the stimulus, whatever it is. That's the big picture. Does that make sense? So that's the difference between the multi-armed bandit and the multi-armed is I'm playing. Okay, so when the multi-armed, I'm playing the game with the nature in some sense, where the nature is not strategically behaving. They just give me the random number. So that's why if I put an arm where that arm has some expectation like 10, but sometimes he gives me 7, sometimes he gives me 12, sometimes he gives me 9, but the overall expectation is like mu. So my goal is to find the arm that has the maximum mu. But the question is that in order to get the maximum mu, I need a sample. Right? But here in this case, we cannot say it's a sample. Well, it's a sample, but it's not coming from a random world. It's coming from a kind of not a complex interaction world in some sense. Because they also run the same algorithm. That's a good question. So Again, the reason I'm asking the question about the connection between the AlphaGo algorithm and this reinforcement learning algorithm, the reason why I'm thinking about the question is the same thing actually. Well, we are talking about probably the same context. Then why can we cannot see the similar algorithm in this text or in that text and so on? So that's something I've been thinking about. Good. All right. Boltzmann-Gibbs learning. This is a very simple slide. Okay? So in the partially distributed algorithm, we have explained. This is a partially learning algorithm, where this algorithm is called, which I call the logic dynamics in the previous slides. But sometimes some people call it like Boltzmann-Gibbs dynamics. That's fine, right? And this form of the function is called the logistic function, where the logistic function's key form is that, well, this is the normalization part, and it's proportional to the exponential function of the payoff, and we have some parameter of 1 over gamma I. But in the previous the previous lecture or the last lecture, we used like beta. Okay, so when the beta goes to infinity, then it is equal to the best response dynamics. When the beta goes to 0, I just randomly choose. Okay? But here in the partially distributed algorithm, what I need to know is the function of the UI, like like other guy's action and so on. Okay? So that's what we do, and we need to modify this algorithm into a purely fully distributed algorithm where we don't know anything about it. We just know the utility of my action, where I don't know other guy's action. So we just replace. See, we just replace this utility as the u hat j comma t h. I don't know other guys. Okay, so this is the utility value that I play aj. Right? Obviously, as you pointed out, in order to run the this dynamics, we need to have a result, or at least an estimation about the average utility of alternative actions, like this guy. Otherwise, how can we compute this guy, right? So the question is that, okay, can I need to play all actions and then get the value of all this guy and then make the normalization? Right? That's a key challenge, right? Okay? So that's why this book uses the word estimation. And all the logistic, the function part, for example, need to overcome this challenge. So do you know the story of the partition function in the machine learning theory, where the partition function is very difficult to compute? The normalization. 머신러닝에서 exponential family라고 하는 랜덤 베리어블의 커넥션 패밀리가 있는데, 거기에 스테이셔너리 디스트리뷰션이 이런 로지스틱 폼으로 표현이 되는 건데, 제일 어려운 게 뭐냐면 밑에 분모의 노멀라이제이션 텀이에요. 그래서 exponential family에서 스테이셔너리 디스트리뷰션을 컴퓨터하는 컴플렉시티가 전부 거기에 집중되어 있어요. 그래서 어떻게 하느냐, 그 approximation 하고 estimation 하고 생 난리를 핀다고. It's the same thing. This is fine, because what we can do is that, okay, if the epsilon j is my constant, and if I play a j, I get the value of the utility. I take the exponential function, but we need to make the probability using this value. How can we make the probability? We need to do the normalization. How can we do normalization? We need to know the value of all other strategies like this number. Okay. So the ninth form of the computing this probability is to, okay, I play all the strategies. I mean, obviously that's inefficient, and that's not practical. So somehow there should be a mechanism that I can make some estimate about this normalization term, and there are some cases where we can make a good estimate and so on. And in many fields like statistical physics, computer networking, machine learning, game theory, all this logistic form, without knowledge about this normalized constants, it's so logistic form of the distribution is a very beautiful distribution. The shortcoming about this thing is that we need to somehow make some estimate about the normalization. Right? If you want to directly compute the probability. Right? So let's read the other things. He makes a decision based on this rough information by using a randomized decision rule to revise his strategy. So once we get this probability, then they toss a coin and select one action and then play it. Okay? This is fine. This is fine when we know the utility functions and other guys' action choices and so on. Okay? But this guy, I don't know the information about other guys. And that's why it's difficult. Because I need to do some experiment or do some action and to get the value. Without that, you cannot compute that. Alright, so let's summarize the fully distributed learning algorithm. Well, in this case, it's good. It's good in the sense that, without much information, what can we do? Okay. Right? And then if you think about the trial error learning, as well as the what's the second algorithm? Second, regret matching, and some reinforcement learning, and also this logistic learning or the Boltzmann-Gibbs learning. They based on the experience utility, and they do some changes about the probability of choosing some action. That's everything. And in that rule, what they are doing is that they actually do this thing. Right? Okay? Whereas in the, for example, Boltzmann-Gibbs learning framework, as it's the same thing for the partially distributed stuff, this algorithm actually does not directly uses the history. Why is that? Because they are based on the idea of noisy-based response. Right? There was a best response. There was a partially distributed logic dynamics. That's the noisy-based response. By including the value of the beta. When the beta goes to infinity, that's equal to the best response. When the beta goes to 0, then it's a random choice. It's a noisy-based response. And then I go to jump to the case where I don't know anything about others. So it's a basically the parameterization starting from the best response to the noisy-based response, where some case I can use some information about others, but in some case I cannot use the information by others. Okay? But whereas like a reinforcement learning, what they're doing is that they use the history, like fictitious play. What the fictitious play is that we count the frequency, right? So like so we look at the number that how many times you choose this strategy, how many times you choose that strategy, and using those histories, then I'm going to adjust my probability. Both philosophies make sense, right? So we can use those intuitions in order to make learning dynamics. And then I'm going to conclude the part of the learning dynamics by highlighting why do we do this. Okay? Again, the learning dynamics, by thinking about the learning dynamics, we are better motivated by the like Nash equilibrium, for example, or the other equilibrium concept of the game. Because by introducing this learning dynamics into the framework, and this is actually what the people or the agent is doing in every step, time step, every day, every time. So by motivating the Nash equilibrium as some convergence point of these dynamics, we're better motivated. That are better motivated. Because we cannot imagine the situation where the people or the players just without any hesitation, they choose the good choice, like Nash equilibrium. Well, it's pretty I mean, it's pretty too ideal, right? Because we are actually thinking about those games in our brain, and sometimes our brain is not perfect. So what I can do is I try first this strategy and update my strategy and probably in 1 month I can find, okay, I can decide, oh, this is a good strategy. This is what we are typically doing in a strategic situation. So that's why we need this learning as an important tool of understanding the game. But more importantly, like rather than better motivation, as an engineer, if we think about why do we need the game theory, we can use the analysis tool as well as the control tool. So if we can use the game theory as a control tool, then probably we can develop a distributed algorithms easily. In that case, what we have to do is that we need to design a game. We need to artificially design a game so that the Nash equilibrium point of that game is a good point, like some optimization point. And also, if we can develop a learning algorithm that converges to that Nash equilibrium, which is equal to the optimal point, that's good. Because we can naturally develop a distributed algorithm. Makes sense? So in terms of those 2 points, the learning dynamics is very important. And this learning dynamics, as you see, like for example, reinforcement learning, that is naturally connected to some machine learning part, which is a hot topic these days. Okay. So like theories and like areas are meet together in some places, and we actually saw the places where the machine learning theory and the game theory actually meets. Okay. There are some places where the game theory meets and optimization theory. Like if we use the game theory as a control tool, right? So there are lots of overlapping areas, and that's why we need to have a very wide background about all the theoretical tools and how can we apply these theories to the practical problems and so on. Okay. All right. So. Basically, I'm going to end the formal lecture about the game theory now. And as I mentioned before, you need to start to think about what kind of, out of two kind of, like course project in some sense, what options you will take, you need to think about them. Alright? So my plan is to meet, I'm thinking about how to make a format. Probably I can meet you individually, like up to the end of the May, about the topic, or probably if you are thinking about some like new papers or the ideas to think about that, I can make some discussion with all of you individually. But there will be some places where we meet together and then probably present some intermediate progress report about, okay, I'm thinking about this problem like 5 to 10 minutes. And then it's like showing some progress to the classmates so that you guys can get some feedback from the classmates. So what's the date of today? That's the 16th?
Yes.
Okay. So let's formally let's meet after 2 weeks. But I will send you an email. So if you want to make an individual meeting with me,